Okay, this is class example program unit C3, page 5. Let's take a look. It looks like this is a fairly big tank. Yes, it is a huge tank. This is 5 feet depth. Although the dimension is not given here, compared against 5 feet, this is probably, I don't know, 5, 6, 7 feet. So this is a large tank, as you can see. So water is siphoned from the tank here. Let's assume this is a large tank. Let's determine the flow rate from the tank. Flow rate is how much volume of water is flowing. And the pressures at points 1, 2, and 3. If viscous effects are ignored. Okay. So this is a siphon problem. First of all, what is siphon? Let's just draw a figure here. So this is, like I said, fairly large tank. This tank is filled with water. Okay? Then you are trying to remove this water out of this tank using just a piece of tube or garden hose, for example. This is a technique called siphon. Why do people want to do siphon? I think the major reason why you want to do siphon is you don't need a pump to do this. It's a very, very cheap way of removing water from a tank. So it's a commonly used technique for example, cleaning up the fish tank. It's a siphon. Okay? You don't have to apply the pump. Okay? So this is a tube, constant cross section, which making this problem a little bit easy to handle. Now obviously this is the surface of the water, so we do know the pressure here is 0 gauge. This is a free surface. Okay. So what's going on here is water is sucked right into this side of the tube and coming out this side. Okay. So I have to first of all draw a streamline because I want to apply Bernoulli's equation to solve this problem. So obviously the streamline is going to be a like flow within the tube, and then the question is, how does the water get into the tube and get out? So starting from here, I'm going to use the dot. This is my streamer. Okay. So this dot represents, this is not constrained flow. So if you pick up one small tiny particle of water, happen to be right here on the free surface, then that particle is going to be very slowly picking up the speed, and sometime later get sucked in here into the pipe. Then as soon as that particle is inside of the pipe, the flow is constrained. So it's a pipe flow. Flow out. Okay? So you have to recognize two different regions of this flow field. This is a constrained flow. So as long as the flow is constrained, you can apply continuity. You cannot here because it's not constrained. Continuity is essentially, if you want to apply continuity here, this is a large tank. Large tank assumption really is if the tank is large, right here on the free surface, velocity is approximately 0 because cross-section area is about infinity. It's a big enough tank so that you can ignore the velocity picked up right here on the free surface. That's why I'm drawing dotted line here. Okay? So, anyways, so I'm going to set up a few points. The program says this is point 1 right here. Right here is point 3. Right here is point 2. Okay? Then I'm going to add a few more points. Right here, let's say point 0. And right here, point 4. I'm going to add 2 more points, point 0 and point 4. And let's apply Bernoulli's equation. Then what I want to do is I want to apply Bernoulli's equation between point 0 and point 4 and see what happens. Okay? So between location 0 to location 4, so you have P0 plus 1/2 rho V0 square plus gamma Z0 is equal to P4 plus 1/2 rho V4 square plus gamma Z4. This is Bernoulli's equation between point 0 and point 4. Let's define height Z. Where do you measure it? Well, let's measure it from here. So this is the height, altitude. If I do that, it is going to make Z4 0. And Z0 is, let's take a look at this one. Z0 right here is measured from here, it's 5 feet. So you do now, this is 5 feet. And other things. Obviously, this is a free surface, this is a free jet. This is 0 gauge. This is also 0 gauge. This is free jet, this is free surface. This is a gauge pressure, so I'm going to use the gauge pressure throughout this analysis here. Okay. One more thing. Of course, this is a large tank. You assume that the velocity right here on the free surface is approximately 0. Large tank assumption. Okay? So what happens to this equation? This equation now becomes gamma times Z0. This is only non-zero component, left-hand side. Right-hand side is 1/2 rho V4 square. So this actually solves you V4. V4 is square root 2 times gamma Z0 over rho. Gamma over rho is a G. So this is square root 2 times G times Z0. Then I stop and think, wait a minute. I think this equation seems very familiar to me. Where did I see it? Well, let's take a look. Where did I see this kind of equation? I'm going to bring you all the way back to this page, page 2. We discussed about free jet velocity. Free jet velocity right here, V2, is essentially square root 2 times G times this H. Free jet equation. That's what you're seeing here. Okay? Oh, wait a minute, this is a free jet velocity. It's exactly so let's just go back and continue. So that means free jet velocity right here, V4, is square root 2 times 32.2 feet per second square, assuming this is the standard sea level gravity, and then 5 feet. So this is going to give you velocity free jet 1794 feet per second. Okay, it's good. So interestingly, this is a constant cross-section pipe or tube. So if you apply continuity equation for the pipe flow between this inlet to this exit, you can say flow rate Q is constant anywhere. Okay? As much as you are looking at flow within this tube, you can say this, because it's constrained flow. Within a pipe, flow rate everywhere is constant. Flow rate is cross-section area times velocity. Velocity right here, we found it. This is a constant cross-section pipe. So what do you mean by that? That means velocity everywhere inside of the pipe is all the same. Okay? This means B1 A1 is equal to B2 A2 is equal to B3 A3 is equal to B4 A4. But A1 is equal to A2 is equal to A3 equal to A4. Cross section is constant. So that means velocity is constant. B1 is equal to B2 is equal to B3 is equal to B4, which is 17.94 feet per second. Is that true? Yes, it is true. So velocity throughout this tube is constant and this way. Good. Continuity says so. Great. So our mission here is to find out, okay, so what is the pressure here, pressure here, pressure here. So let's apply once again Bernoulli's equation. You can apply Bernoulli's equation between any location, between any point, between 0 to 4. Okay? Bernoulli's equation is not constrained. Only continuity equation is constrained. So continuity equation can be applied between inlet to the exit of the pipe only. Bernoulli's equation can be applied any location in between any two locations along this streamer. Okay? So let's apply Bernoulli between point 1 and point 4 to find out pressure at point 1. So you can say P1 plus 1/2 rho V1 squared plus gamma Z1 is equal to P4 plus 1/2 rho V4 squared plus gamma Z4. Okay? Now one thing you can tell, of course, is, like I said, this is a free jet, zero gauge. And Z4 is 0 because we measure Z from location 4. Z1 is, this is 5 feet and then is another 3 feet, so this is 8 feet. B1 is, we know, B1, B4, it's the same thing, so we can drop it, right? B1 is equal to B4. Constant value, so it's subtract each other. So that leaves you P1. P1 is equal to minus of that, minus of gamma Z1. So pressure P1 seems to be lower pressure, in other words, minus pressure. Minus pressure, So this is less than atmospheric. So negative gauge value, that's what you expect to have. Gamma times, what's this? Depth or height? What kind of equation is this? Wait a minute. I stop and think, hey, I've seen this equation before. What is this equation? This is purely hydrostatic pressure variation, right? Oh, okay. So it's like a lower pressure because it's shallower. That's it. So how much shallower do you have? Do you have 8 feet shallower from here to there? This is a zero gauge, so this is essentially that much vacuum pressure. Hydrostatic. Oh, interesting. So let's finish up. So this is minus gamma, which is the specific weight of water, is 62.4 pounds per cubic foot. Z1 is of course 8 feet. So this computes minus 499 pounds per feet square, PSF. Negative sign means this is really lower than local atmospheric pressure. So this is PSFG. So minus 499 PSFG. Really low pressure. Oh, okay. So let's repeat the same thing to find out the pressure at point 2 and point 3. Now, if the point 1's pressure is purely hydrostatic, those two are also. Okay. So let's apply Bernoulli's between, I don't know, 2 and 4. You ended up having same exact equation. You are going to have a P2 is equal to minus gamma Z2. Right? Z2 is measured from here, 5 feet. So this is minus 62.4 pounds per cubic foot times 5 feet, which is minus 312 pounds per square foot PSFG. Oh. So you can repeat the same thing between Bernoulli's between point 3 and 4. You can have similarly. Okay. P3 is essentially minus gamma times Z3, which is the same as that. Oh. So pressure at location 2 and 3 are the same thing because it's in the same depths, same water, it's hydrostatic. So here's a conclusion, and then it's an interesting observation how the siphon works. Siphon is very interesting because you can remove the water from the tank using siphon. Lots of people do that. What is the mechanism of water flowing inside of this tube without any pump? First of all, when you start siphon, for example, today is the day that you need to clean up your fish tank. Well, I hate to do this, but I have to do it. So you are going to pick up a siphon, which is essentially the tube. Okay? So you dip one end of the tube inside of the fish tank right here. The other side of the tube, you drop it on the ground. That's it, right? Water flows. Water flows. No, I don't think so. I have to do something to make the water starts flowing. Okay, so this is a very classical, actually dumb way to do that. You pick up the other side of the hose and then water comes up and then remove it. Then burn, you establish the cycle. What are you doing is basically making a suction here by creating lower pressure. So suck the water in up to this point, then you release it, then the rest of it is essentially the gravitational acceleration takes care of the flow. Okay, and that's the cycle. So this is the low pressure point, this is a zero gauge. So between those 2 points, because of the pressure difference, low pressure suck the water up to this point. Okay. Then from here to there, this is a low pressure, this is high pressure, but because of the gravity, water drops off. So this is a gravitational acceleration driven flow. From here to there is a pressure difference driven flow. So once you establish that, it is going to keep going without needing a pump. That's called cycle. Okay. So nowadays, if you visit Walmart, you have a special device, cyclone device for cleaning up a fish tank. Some of them actually comes with small tiny hand pump in the middle here. So you have then creating low pressure, pump up the water a few times. Then once you pump the water down once, then you don't have to do it anymore. You just release it, water flows continuously without doing pumps. Okay? So you can either do or you can do pump. Either way is fine. Okay? So this is interestingly very fundamental application of Bernoulli's equation together with continuity. That's it.